This problem is a ramp problem that comes from a different book. And because you see in the problem it talks about the skier coasting at a constant velocity, then we're going to, we know that it's at equilibrium and all the forces will cancel. And we start by drawing the free body diagram. So I'm going to do that here. I have the skier, who I'm not going to draw. But I'm going to represent the forces on the skier. I know this angle is 37 degrees. Actually, let me write that so it doesn't get in my way. So this is 37 degrees. Okay, and we, of course, have the skier's mass that is being attracted by planet Earth. And so we draw the force of gravity here. It's asking about friction, so we must be considering friction. Sometimes we ignore it. But I'm going to draw that. And I know that because the skier is not applying a force anymore, like she's not pushing off the ground, she's just coasting. And so there are really only three forces to consider here. Gravity, that's what keeps her moving down the hill. Friction, which resists her motion down the hill. And then the normal force, which resists her falling down through the center of the earth. So I'm going to draw the normal force and the force of friction. And the reason I stopped here is because when I draw the force of gravity, that's kind of setting things up. I have to scale my other forces based on how long I drew that first vector, if I'm really going to make this an equilibrium case. Now, I'm going to, because the normal force is going to go perpendicular to the hill, and the force of friction is going to go parallel to the hill, if I try to draw those on here, you know, they're not on my grid as nicely. So what I'm going to do is rotate my XY axis here so that it's parallel to the hill. That makes it so two of the three forces are like along the XY axis. You don't have to do it that way. It's but that's the way to make the math easier. So here I'm going to draw the normal force, and I have to draw it so that it cancels with the part of gravity that would want to pull the skier like through the snow, so to speak. So I'm going to just line up. I have a new y-axis along this black line. And I'm going to make a new x-axis along the hill. Okay. And looking at the way I drew my gravity vector here, then I'm going to try to draw this to scale. So I can see that the force of gravity has two parts now. It has a component that goes along my new y-axis. And then it has a component that pulls the skier down the slope. That's that part. It's all kind of cluttered now. Okay, but then I know, because I'm in equilibrium, that the normal force must be canceling with gravity, and I'm going to try to draw it the same length. It's like about 5.5. So I've got a normal force here, and then the force of friction is pointing just a little bit this way, resisting her motion down the hill. Okay. And I should see that, for instance, if I could move, maybe I could show, see how those are the same length, that my x components are going to cancel, and then my y forces are going to cancel as well. Okay. Well, I'm trying to find the coefficient of kinetic friction. That requires me to know both the force of friction and the normal force in order to calculate that. I don't have formulas for those, since I can't really solve for it for the force of friction using the coefficient. That's what I'm finding. But I do know the mass of this person. So I know 62 kilograms here. And that lets me solve for the force of gravity. So I'm going to solve for that first. And I get 62 times negative 9.8 newtons per kilogram. Do that real quick. Okay. And I don't know how many sig figs. It looks like I should only keep 2. I'm going to keep 3 just for grams. So I get 608 newtons, which is down. I'm leaving the negative sign there. Okay. That is not an X or a Y force, right? Because I just shifted the XY axis. So that's actually a force that goes straight down. And I need to find the part of that that goes against, or that would cancel with normal force. Okay, so then let's look at the sum of the forces in the Y direction. My new Y-axis, okay? That has to be 0 because we're at equilibrium. And the sum of the forces in the Y direction are the part of gravity that points down in my new Y direction plus the normal force. Okay. And so using trig, I can do that. Now, it's important for me to point out, and I don't remember the geometry proof, so to speak, of this fact, but if there's a 37-degree angle between the horizontal, like what we would say is straight horizontal, and my new x-axis, then there's also a 37-degree angle right here between we would always call vertical and my new y-axis, and that's important to know. So this angle I'm showing right here is also 37 degrees. That means that if I want to find FGY, okay, that would be this guy right here. Let me grab this vector. So I'm talking about this one right here, okay, that lies adjacent to my 37-degree angle. Okay, so if I solve for this, I'm saying I know that the hypotenuse, which happens to be the force of gravity, times the cosine of 37 degrees would give me that adjacent side plus the force I'm looking for. So once I plug in my information here, I know negative 608 newtons times cosine of 37 degrees plus the normal force would have to sum to 0. Okay, so if we calculate that, we get that the normal force then must be positive or up 485 newtons. Okay, that's one piece of the puzzle. And then the next step is to use the x direction to find the force of friction, the blue one here. So if I do that, I know that the sum of the forces in the x direction is also 0. And the only two forces I have in that direction are the force of friction and the part of gravity that is in the x direction pointing downhill. That's what's causing or keeping the skier going downhill. So here we have, again, using some trig, right? So I'm saying I know the hypotenuse, and I can use the sine of my 37-degree angle to get the opposite side. Okay, so when I set that up, and I've got a plug and chug here. And I get a frictional force of 366, looks like, newtons. Now, technically, you know, which one's positive, which one's negative? On my picture, I would have called the friction a negative force. But in a minute, we're going to take the absolute value anyway. So maybe I'll just write myself a note, like, okay. Now, on your formula sheet for the AP test, it has, you know, a more general formula, because it looks like the absolute value, the force of friction is less than or equal to coefficient of friction, and they use F sub n for the normal force, okay? But that's great. That's how I'm going to solve for mu, which is what I'm looking for. And what's encouraging is that the force of friction is a lower number than the normal force, which it is supposed to be. It is always, you know, a fraction of normal force. Mu is always between 0 and 1, okay? So now I have 366 newtons. And in this case, I'm dealing with kinetic friction. That is an equality, okay? And then I have my, I already forgot the number, 485 here. Okay, and then the proportion of these here comes out to be about 0.75. And notice that the newtons cancel. Coefficient of friction is just a proportion. It has no units. Okay, so for these ramp problems, the idea is to often shift or twist the axis so that most of your forces line up either on the y or on the x, and you only have to deal with the trig for like one of the forces.